Welcome everyone to today's talk on open trust analysis. My name is Susnata Chattopadhyay and I am a second year BSMS student here at ISER Kolkata. Today I am going to present the uh, compu- minimum theoretical and computational concepts that are required to get going in performing data analysis of any open cluster. In this talk, we'll cover a brief introduction. What are star clusters? What are they? Which data did we use, and the methods that are used to identify the cluster members, and a powerful method to estimate their parameters. This is MCMC sampling. So, and we end by with our concluding remarks. Star clusters are pretty much agglomerations of stars. Some have a prominent globe-like appearance, while others do not have a defined boundary. As you might already have guessed, they are called open and globular clusters. What are globular clusters? They are the senior citizens of our galaxy because they were formed only once in the galactic halos during the formation of galaxies themselves. They are massive in size, they contain huge number of stars, approximately 10,000 to a million stars. They are more luminous, red and yellow stars. They comprise of red and yellow stars because they are older. As you can already see in this picture, it's it has a very massive core with lots and lots of stars, and majority of the stars are reddish in color. They also have chemically weak absorption lines of metals. You might have already know that in astronomy, every element heavier than helium is called a metal. So why is it so? As they were formed very early in the universe history, they were formed from the remnants of the stars which didn't have enough time to synthesize heavier elements. So they are metal poor. What are open clusters? They have, as I have told already, they have an diffuse morphology. You cannot make out a clear boundary of open cluster. They arose from a larger, more diffuse affiliations called the stellar associations. So they have a homogeneous nature. They have the same age, same distance, more or less the same distance and chemical composition. And unlike they began from a single molecular cloud. And unlike globular clusters, they continue to form today in the galactic disk. Open clusters are hot, young, blue, and dynamic stars. They are less luminous because they are present in they are present in the galactic disk, which is a site of heavy star forming region, star forming activities. Henceforth, they are obscured by lots of gas and dust, which makes them difficult to observe in the visible. They are metal rich because they are formed from the remnants of massive stars. Data used. In our project, we have used mainly the data by European Space Agency's Gaia mission. It consists of 5-parameter astrometric solutions which are limited to G21 mag and a Gaia photometric band which consists of G, GBP and GRP, which G ranges from invisible to near infrared, GBP acts on the blue band while GRP specifically focus on the red band. In the 5-parameter astrometric solutions, we have RA deck, alpha delta, PMRA, PM deck, which are the proper motion components, and the parallax. The errors in our data are photometric uncertainties of about 6, 108, and 52 millimag at G20 max. Proper motion errors about 0.02 to 0.03 at G9 to 15, 0.07 at G goes to 17, 0.5 milliarc second G equals to 20 and 1.4 milliarc second at G equals to 21 magnitude. We also have used the data from TUMAS. TUMAS is a ground-based infrared survey conducted at Chile and USA. It it also it operated in primarily in 3 infrared bands: J, H, and Ks. Okay, now consider the wavelength band G. Then we have Mg is capital Mg plus 5 log base 10 d by 10 parsec plus Ag, where Mg, small mg is apparent magnitude, capital Mg is absolute magnitude, which is the apparent magnitude of a star visible when it is kept when it is at a distance of 10 parsec from Earth. And Ag refers to the term extinction. So, what is extinction? Extinction is caused by the interstellar dust. The space is not empty; it's filthy. Uh, it is filled with rarefied but very filthy gas. If this were compressed to the density of air in the room where I am speaking, then I wouldn't be visible to someone standing 2 meters away. Reddening is caused by the interstellar dust. How? Those Trumpler in 1920s realized that this dust and smoke obscures majority of the stars in the galactic disk, where most open clusters are. They not only dim but also reddens it. It follows the Rayleigh scattering law, which states that the scattering intensity I is proportional to 1 by lambda to the power 4. So, a star obscured by the dust, most of the blue light which have a lesser wavelength will have a higher intensity of scattering and so will be scattered away, leaving only the red light behind. As you can see from the picture, the stars which are deep inside this huge dust cloud are reddish in color. Mathematically, extinction is defined as Ag, which is m minus m naught at G at some wavelength band G, where m is the apparent magnitude that we observe, and m naught is the magnitude of star that would be observed in the absence of dust. Color excess and reddening is referred to the difference between the observed color and the intrinsic color, which is, say in some colors, say BPRP, E BP minus RP is m minus m naught BP minus m minus m naught RP, which is nothing but ABP minus ARP. Now, the most crucial step in any analysis is how to select the good quality data. So it is important, and how do we know how to determine that data quality is good? It is important to know where does my data come from. We should always read the documentation. For example, the most frequent restriction that we can employ in our data sets are positive parallaxes which are not null. Parallax, this is because in Gaia certain parallaxes are negative, which are caused due to instrumentation biases. For a good quality astrometric solutions, for good quality astrometry, we require parallax over error to be greater than 5 or 10. This is nothing but the signal by noise ratio. The absolute, as we will see in the later part of the presentation, we will be performing clustering on proper motion space. For this reason, we require good quality proper motion value. So we need absolute proper motion PMRA and PMDEC errors to be less than 0.5 milliarcs. Now, of course, PMRA and PMDEC should not be null. And a new feature that is added in Gaia DR3 is RUWE. RUWE cut of less than 1.4 ensures that each data point is indeed a single star and not an unresolved binary. Step 2. We perform a 1 to 3 sigma clipping of data about median PM. Now, why median? This is because median is more robust to outliers. Suppose we have a CCD with pixels reading photon flux values like 100, 21, 22, 23, 24, say 20. If we take the mean of all the values, the term of 100 will affect the true value of the photon flux. This is because The mean takes in account all the data values, but the median will be close to 20, which is the true value of 20 or 21, which is the true value of the photon flux that we are trying to estimate. And how many sigmas? It depends on the value of the sigma. So large value of sigma, if for our data the standard deviation is large, we should proceed till 1 sigma cut. While if it has very low sigma, we can take up to 3 sigma cut. So why is it used? It is used to remove the high proper motion foreground star. Let us see how. Okay. So in the picture on your left, you can see a proper motion vector plot of all the sources. If you see closely, there are quite a number of stars which have high proper motions in random directions. These are indicated by the blue and green yellow arrows. After we perform the PM cut, we can easily chop off the values which are spurious, like the high proper motion foreground stars. What remains with us is a mixture of our cluster members and the background field stars. We then proceed to clustering. In our analysis, we perform KNN followed by DBSCAN velocity point diagram of filter data. We expect all the cluster stars to have similar proper motion. There is also a popular method known as HDBSCAN, which we will discuss later. KNN. KNN stands for kth nearest neighbor algorithm. We implement the nearest neighbor function by scikit-learn. As we shall see later, DBSCAN requires us to estimate two input parameters, which are min points and epsilon. We determine the optimum value with the help of KNN algorithm. How do we do it? The optimum value of epsilon is estimated by a k distance graph, where we plot the average distance of each point to its k equals to min points nearest neighbors. So for each I in the scatter plot or the data set, so if n is the total number of data points on which to perform a clustering, I will run for 1 to n. So here d1 is the distance of that data point to its nearest neighbor. D2 is the distance of data point to its second nearest neighbor, and so on up till dk. All divided by k because we need to take the average of all the distances. The ideal value of epsilon is generally taken to be optimum at the distance value at the knee point or the point of maximum curvature. This is because this point represents the point of inflection between two states of data. On either side of this point, the clustering behaves differently. So in this k distance plot, we can see the knee point is approximately 180, which corresponds to an epsilon value of 1.1883. DBSCAN. DBSCAN stands for density-based spatial clustering of applications with noise. Unlike k-means clustering, which partitions the data into one or more clusters, DBSCAN is more effective because it is based on the intuitive notion of clusters and field noises. It requires two input parameters, min points and epsilon. Let us go over briefly the algorithm to understand this. So consider we have two data sets, X and Y, and the data are scattered in the scatter plot. Okay. So we enter before initializing our clustering ensembler, we enter the parameters epsilon and min points. The model reads each data point in X and Y and stores it as an XY 2D array. It determines the density code points among these coordinates. How does it do? We start with each point P, let's say XPYP in the scatter plot. We take an epsilon neighborhood circle around it. And if it's multidimensional, let's say we want to cluster four or more data points, we'll take an epsilon neighborhood ball. If the ball overlaps with we take an epsilon neighborhood ball. Okay. If the ball overlaps with greater than or equals to mean points number of points, then it is marked as a core point. We proceed in this way to the rest of the data set. We proceed to this point, then this point, to this point, to this point. At the end, what we will get is all the points are marked into either core or non-core points. We then pick one core point at a random. Let's say we pick this point. And again, we similarly, we draw an epsilon neighborhood circle around it. Let's say the green points are the core points previously marked. Then all the core points which overlaps within this neighborhood are assigned cluster 1. We continue in this way until no nearby core points are left. Now imagine we have we have now got a preliminary cluster. Now there will be few points remaining which are not core points. Like this. These were not marked as core points earlier. What we next do is we take in all the nearby core points, only the first nearby ones into the cluster and exclude the rest. We have now got our first cluster. Now for core points which are farther than epsilon, we are using note that we are using Euclidean matrix. Then cluster 1. So this is cluster 1. So points that are here are farther than epsilon. So this we assign cluster number 2. We repeat the same step similarly. We notice that the clusters are created sequentially. Finally, the points which are, say there were some points here. So they were not included in any cluster. They are marked field or outlier. Today, HDBSCAN. HDBSCAN is hierarchical DBSCAN. We are not going into detail, but if you want to know more about it, we consider looking through the documentation. You can understand it briefly. So unlike traditional DBSCAN, which has a fixed epsilon value, HDBSCAN performs DBSCAN over varying epsilon values and integrates the results to find the clustering that gives the best stability over epsilon. This allows HDBSCAN to find the cluster members of varying densities and be more robust to parameter selection. Now, the penultimate step, probabilistic models. After we are done with clustering to select the preliminary cluster candidates, we proceed to implement the probability models as suggested by Mr. B. N. et al. 1998. We define phi VC, the velocity distribution of the cluster stars, phi VF, the velocity distribution for field stars, phi RC, surface number density of cluster members, phi RF, the uniform distribution of the field stars. Okay, so these are the formulations of those quantities that we defined. Note that these all are arrays of numbers. The x and y refers to array and deck respectively. Mu xi and mu yi refers to the proper motion components along x and y axis, which are array and deck. Mu xf and mu yf are the field centered proper motion component. Mu yc and mu xc are the mean cluster proper motion centers. Sigma c is the intrinsic cluster dispersion, PM dispersion. Epsilon xi and epsilon yi are the respective PM errors of the cluster stars. and gamma is the correlation coefficient, RC is the characteristic radius, and R max is taken as the maximum queried radius. So we have defined here all the terms. So sigma C is how to calculate sigma C. It is called the intrinsic PM dispersion. It is defined as in sigma C square equals sigma naught square minus 1 by n sigma I zeta I square, sum over all zeta I square, where n is the total number of preliminary cluster candidates, and zeta I is epsilon xi plus epsilon yi by 2, which is the average of the observed errors of proper motion components, and sigma naught square is the normal standard deviation of the proper motion. The distribution of all the stars can be described as follows. So the total distribution phi I is nothing but NC phi RC phi VC I plus NF phi RF phi VF I equals to phi C plus phi S. Note that if I data point belong to a cluster region, then automatically the second term would be 0. And if I belong to the field region, then the first term would be 0. So NC and NF are NC plus NF equals to 1 as the normalized number of preliminary cluster and field stars. Now the total probability is then computed as P mu I is phi C I plus phi I. We tend only those stars as most probable candidates which have probability of P mu greater than 0.5 or 0.9 as desired. But if we still find contamination to exist in the color magnitude diagram, the only design behind this is similar proper motion of both cluster and background stars. So, what is the solution? It is pretty clear that velocity-based clustering is failing. Our final weapon against this is FSD. We implement the FSD model as given by S.R. Dhanush et al. 2024. FSD stands for field star decontamination. Note that before trying to understand it, we note that this method is not used to find any cluster member, but to rather remove the contaminants in the CMD on the basis of the similar photometric property with that of nearby field regions. The stars we get by this method are the maximum that can be obtained statistically. So we look at this diagram carefully. First, we take a radius r which is equal to half of the angular size of the cluster as found in literature. So we name this region as cluster candidate. Now we choose another radius r1 such that the area of this annular region equals to area of the cluster region. Why? This is because we are assuming here the density of field stars, surface number density of field star is more or less constant. So taking equal areas of annulus will give roughly the equal number of field stars to compare with. We proceed in this way. So we select radius R1 so the area of the annular region is equal to the inner circle. We name each of these cluster field annular regions as field 1, field 2, field 3, field 4, and so on. Note that we have used the Haversine formula to calculate the angular distance between 2 points, RA and X. Now, keep in mind that it must be in radians. Now, we plot the GBPRP, the apparent color magnitude diagram of field N and cluster candidate side by side. Field N can be said the first field, first annular region, cluster 1, field 1. Now, take one data point at a time from cluster candidate. Suppose this is the data point, and we consider color magnitude bins with different sizes starting with delta G. So this is delta G. This is delta G BPRT. We search, now what we do is we search for its closest counterpart in the field diagram, field and data point. If we fail to find any matches, we increase the bin size to a maximum of 0.5 to 0.25 iteratively to search for the closest field star counterpart. So you can think of a process by which we can make this easier, faster. Now those with counterparts in the field CMD, suppose we find a counterpart in the field CMD. One lies here. Let's say we find one lies here. What we do is we take the nearest field counterpart, and remove both the field star and the cluster star from the data. Okay. The star and the counterpart are both removed from field N and cluster candidate CMD. So if no matches are found, we proceed to the next field region and apply the same steps. Now, so after this process, what we'll get is statistically the most number of stars that can be obtained in a highly crowded region of the galaxy, of an open cluster situated in a highly crowded region of a galaxy. Now, how to estimate our parameters? In any astronomical data analysis, we are required to fit our data with a certain model by estimating the unknown parameters. A very powerful way to achieve this is through MCMC sampling. MCMC stands for Markov-Chain Monte Carlo. We are going to use the EMC4 Python package for implementing Markov chains. The Markov chain Monte Carlo fitting isn't quite fine about finding the absolute best fit for a model, rather understanding the probability distribution of the possible fits. Now imagine a rough landscape where valleys represent good fits and hills represent bad fits. MCMC stumbles upon this landscape favoring valleys, but occasionally going uphill to explore. It works by creating a kind of random walk through possible parameter values of your model. The sampler, the chain, which is produced by the sampler, it roams about the minima, but we never approach it. By taking many steps, MCMC builds a map of where the good fits are likely to found. So think of it like this. We start our sampler, say here, it goes to this position and then samples another value, let's say here. This is the parameter space. And let's say our perfect maximum likelihood parameter, maximum, like our most optimum value of parameter is here. Let's say the sampler chooses this value of parameter. If the probability of going to this region is less than that of this probability, then it will ignore this point. Sampler again chooses the value of parameter, let's say here. We see if we find that the probability of going here is greater than the probability of coming here from here to here, the sampler will go here and then the other chain is formed. It continues this way after taking some steps until it finds the minima and it roams about it like this. These initial steps are useless to us. These are called burn-in steps. Burn-in. So this walk is informed by how well each parameter set fits our data. The better fitting sets having a higher chance of being chosen for the next step. This is also called Metropolis Hastings algorithm. So it's a good practice. We should exclude the initial burn-in steps, approximately 1000. This map, which the MCMC sampler produces, is called the posterior distribution. It tells us not just the single best fit, but also how likely other possible fits are. In this presentation, we explain MCMC by taking an example of King 1962 profile to calculate the structural parameters of a cluster. From Bayes' theorem, we have P theta given data and model equals to probability of data given theta and model times probability of theta given model and probability of data given model divided by the probability of data given model. Here theta is the parameter vector. The term on the left is called the posterior. This quantity is known as the likelihood. This quantity is known as the likelihood. This is the prior, and this is called the evidence. The likelihood is what we seek to maximize via maximum likelihood estimation. Prior, which is often denoted by pi, encodes any previous knowledge that we may have about the parameters, like previously studied results in literature, physically acceptable ranges like non-negative values, etc. And evidence is just the total marginal likelihood. See that it's not dependent upon theta, so we can safely ignore it as a scaling constant from now on. Our model is FR given FBG plus F0 by 1 plus R by RC square, where RC, FBG, and F0 are cluster coordinates, background density level, and central density level, respectively. The parameter vector theta is comprised of the three unknown parameters, the F0, FBG, and RC. But data is DI, where D consists of DI element, and DI consists of Xi, Y, and sigma I. So Xi is the position of the center of the radial bins. Yi is the corresponding number density of stars within the field annular region. And the error sigma I is defined as 1 by root Ni, where Ni is the star count in each bin. Now, how do we define likelihood? We generally assume the data to be normally or Gaussian distributed about the model. So for each data, we multiply it the Gaussian distribution. So L is the continued product I 1 over root 2 pi sigma I square e to the power minus delta yi by 2 sigma I square. Here, uh, here delta yi is equals to yi minus f of, this is the model which takes in xi at a given parameter. Delta yi is called the residual. However, it is often convenient to work with the log of exponential quantities. So we have ln L is minus half sum over ln 2 pi sigma I square plus sum over delta yi by sigma I whole square. We implement this in Python. So we define a function log likelihood. It is it takes in the values theta, r, density, and density error. F0, FBG, and RC are the unknown parameters, and we take this value from theta. Model is the king model 2 that we defined earlier, and sigma 2 is this actually sigma square, density error square. So this is how we define code. Now, for better convergence of chains, we construct a uniform prior for RC and F0, while a Gaussian prior for FBG. The following code will make it clear as we define log phi. So we want a uniform probability distribution RC and F naught. So if F naught is between 0 and 50, RC is between 0 and 20, and FBG is greater than 20, note that we obtain these bounds after studying the literature. And we take a log prior of FBG as a Gaussian prior, Gaussian distribution distributed above the mean FBG and sigma FBG. These values are obtained from an earlier literature value of the cluster. We return it as 0 plus this log of this probability. So normally a prior will have multiplication and probability of F naught times probability of RC, which both are constants, and probability of FBG, which is Gaussian. So after taking the log, we'll have the product separated into sums. So the sums of the constant will again be a constant. So we combine both these constants can scale it to 0. So it doesn't matter whatever value we take. And the sum we add the log prior of FBG. So if it's not there, we have pi is 0. So log of pi is minus infinity. Constructing posterior. So as I already mentioned, we can ignore the term in the denominator, which is called evidence. So log p is approximately log L plus log pi. As the evidence is not dependent on parameters, we can safely exclude it as a constant. So def, we can easily see we have defined the function log probability, and if it is finite, then only we return LP plus log. LP is prior, log likely. Now maximum likelihood estimation. We seek to maximize the posterior, which means maximizing the log of likelihood, because posterior is actually log p. So maximizing log p means maximizing log L, as log pi is constant, and which means minimizing minus log L. We'll use the minimize function from SciPy to optimize library. We define NLL to be the minus log likelihood. We give an initial estimate of the values, and then we run our minimize function, giving the arguments are being centered, radial density, and density error. The solutions that are obtained are F naught ML, FBGML, and RCM. Now we initialize the sampler. To reduce the burn-in steps drastically and ensure rapid convergence, we start the sampler in a tiny Gaussian ball POS around the MLE parameters for the MLE estimate for the parameters. So what is happening? We are specifying the number of dimensions as 3, which is M. Number of walkers to be 24, 8 per parameters. Now we think of the walkers as the fingers crawling out of each hand on the manifold or surface of each parameter. So let's say if I have 2 walkers, then per parameter, 2 fingers will crawl out and make the chain, and so that it will converge along a specific point, which is the maximum likelihood estimation of those parameters. And each walker is progressing towards the optimum values after each step in the parameter space. So it is the code. We discussed the first 2000 elements as the burn-in steps. The final parameters and the errors are obtained by F naught MC, is the median of the samples. Now, how to find the ideal number of walkers? A general rule of thumb is to have 2 into n dimension, where n dimension is 3 number of walkers. More walkers improve the exploration of the parameter space and convergence of the chains, but at the expense of computational burden. Visualizing. We plot corner plots for our visualize MCMC fitting. The corner plot displays all 1D, 1 and 2D projections of the posterior probability distributions of our parameters. It is beneficial as it swiftly reveals the covariances between the parameters. To find the marginalized distribution for a parameter or a set of parameters in MCMC chain results, we project the samples onto that plane and create an n-dimensional histogram. Consequently, the corner plot presents the marginalized distribution of each parameter independently on the histograms. This is a marginal distribution. As we can see, it has a center. We're taking the median values and the marginalized two-dimensional distributions on either panels. This is between FG and F0, this is between RC and F0, this is between RC and FBG. Note that closed sinusoidal density plots indicates a successful convergence of all the parameters. Why use MCMs? What's the big deal here? Well, let's see the big deal. Robustness, it has a very lot of advantages. First of all, robustness in complex models. MCMC handles non-linear and high-dimensional parameter space effectively, managing complex models where traditional methods may fail. Comprehensive uncertainty quantification, it provides full posterior distribution and credible intervals, offering a detailed understanding of parameter uncertainties. Incorporation of prior information, it naturally integrates prior knowledge about parameters. It is useful in cases with sparse or noisy data. It is not possible in ordinary least squares fitting. Exploration of multimodal distributions. It's capable of finding multiple peaks in the likelihood surface, ensuring thorough exploration of the parameter spaces. And adaptability and customization. Customizable algorithms, example metropolis testing, deep sampling, and reliable convergence to true posterior distributions. So, to conclude, why study open clusters after all? As we already saw, it gives an homogeneous samples. All stars in open clusters have similar ages, distance, and compositions, making them ideal to study the effects of extinction. Dynamic environments. They are young, dynamic, and unstable, thus provide insight into high-speed stellar processes. Testing theories. Open clusters are very useful test beds for theories of stellar evolution, challenging and refining our understanding. Extrapolation. By examining nearby open clusters, we can easily extrapolate findings to understand far away massive galactic clusters on a large scale. So that's all. Thank you.